Assalamu alaikum, it's me Ms. Faradiba from Peshawar Model School, Nashera branch. Today we will discuss our fifth lecture, which is the derivation of the expression for equilibrium constant, and this is from unit number 9, chemical equilibrium. Look at your book, it is from page number 8, the derivation of the expression for equilibrium constant of a journal reaction, which is from unit number 9, chemical equilibrium. But before going to discuss our topic, I would like you to subscribe our YouTube channel so you will watch our upcoming videos. Okay, let's come to our topic. The equilibrium constant Kc is a mathematical relationship that shows how the concentration of the products vary with the concentration of the reactants. What does it mean by this relationship? This relationship shows that if the concentration of reactants are higher, so automatically the concentration of the product will be higher, and if the concentration of products are more, so the concentration of reactants will also be more. As we discussed in our previous topic, that rate of forward reaction is equal to rate of reverse reaction. So what does this mean? Rate of forward reaction means that if the reaction goes in the forward direction, it means more products are formed, and if the reaction proceed in the reverse direction, so it means that more products are reacting back and give us the reactants. So this mathematical relationship means that the concentration of both reactants and products are changing simultaneously. It can be derived by using the rate of forward reaction and rate of reverse reaction. As we discussed in our previous topic, that rate of forward reaction is equal to rate of reverse reaction, and what was the value of RF and RR, as we know very well that RF value was the Kf concentration of A, concentration of B, and RR value was the Kr concentration of C and concentration of D. Okay, by rearranging the above equation, we get that Kf by Kr is equal to concentration of C and concentration of D divided by concentration of A and concentration of B. This is our equation number 2. Okay, this Kf by Kr is equal to Kc. What does it mean by this Kc? Kc means the equilibrium constant. It also means this part of the equation number 2. We can write this equation like this: Kc is equal to concentration of C and concentration of D and divided by concentration of A and concentration of B, which is actually the value of this Kf divided by Kr. Okay, why we wrote this concentration of C and concentration of D in place of Kr? It means that Kf is stand for the rate of forward reaction, and rate of forward reaction means that the reaction which goes in the forward direction and will give us the product C and D. It means that this is the value of Kf, the equilibrium constant for the rate of forward reaction, and this is for the Kr. Kr stand for concentration of A and concentration of B. Why? Because this is for the equilibrium constant for the rate of reverse reaction. Why it is for the reverse reaction? Because these products are reacting back and will give us these reactants. So that is why Kr is for concentration of A and concentration of B, where Kc is called the equilibrium constant. This is called the equilibrium constant. In Kc, the subscript C denotes the molar concentration at equilibrium, and in this Kc, this subscript denotes the molar concentration at equilibrium, that how many moles are reacting. The general definition of the equilibrium constant can be stated as: the equilibrium constant Kc is the ratio of the mathematical product of the concentration of substances formed at equilibrium to the mathematical product of the concentrations of reacting substances. Okay, this definition means that this Kc is the in Kc is the equilibrium constant, is the ratio of the mathematical product of the concentrations of substances formed. These are the substances formed, which means the products formed at equilibrium stage, to the mathematical product of the concentration of the reacting substances. These are the two reacting substances which are reacting together and will give us this product. Each concentration is raised to the power equal to the coefficient of that substances in the chemical equation. The equation for Kc is sometimes referred to as the chemical equilibrium expression. Okay, now Kc is equal to the product of concentration of products raised to the power of coefficient divided by to the product of concentration of reactants raised to the power of coefficient. Okay, this equation we will explain by the some journal example, or we can say the journal reaction. Okay, let us consider a journal reaction with different number of moles. So the law of mass action can be applied as, okay, this is the journal equation. This is the journal equation. These are the subscript. This is the subscript for A, and this is the subscript for B. This is the subscript for C, and this is for this D. Okay, where A, B and C are the molar concentration of A, B, C and D respectively. The equilibrium constant expression can be written as, okay, now you can see, you will identify that how this definition or this equation stand for this journal reaction. Product of concentration of products raised to the power of their coefficient, to the product of concentration of the reactants raised to the power of coefficient. Okay, large value of Kc shows that at equilibrium the product concentration are greater than those of the reactants and vice versa. The equilibrium constant of the reaction is independent of pressure, concentration and catalyst, and its value is constant for particular reaction. Okay, what does it mean by this sentence? The large value of Kc shows that at equilibrium the product concentration are greater. It means that this Kc or equilibrium constant is directly proportional to the concentration of C and concentration of D, which are the product of the product substances formed, or we can say this is directly proportional to the products formed. So if these products are more, so the equilibrium constant will be higher. It means the rate of forward reaction are faster, so this equilibrium constant will be, or the value of this equilibrium constant will be greater than those of the reactants. Okay, we can also see this large value of Kc. A large value of Kc shows that at equilibrium the product concentration are greater than those of reactant. Small value of Kc, what does it mean by this? The small value of Kc shows that at equilibrium the product concentrations are smaller than those of the reactants. It means that the rate of reverse reaction will be higher than the rate of forward reaction, because the equilibrium constant is inversely proportional to the rate of reverse reaction. Okay, this was all for the derivation of general expression for equilibrium constant of a general reaction. Okay students, I hope you will like this video and you will understand this topic with me.